Hey everybody, let's continue with waves. In this one, I just want to talk about three aspects of waves. Reflection, and we could do the law of reflection. Refraction, and we'll get to the law a little bit later, it's a little bit more complex, but explaining why refraction occurs is straightforward. And then another effect called diffraction. So we want to look at these and look at them both in terms of sound and light. So let's start with the law of reflection, okay? So the law of reflection is pretty straightforward. It's sort of like how a mirror works, but it's also how an echo works. But with a mirror, we could explain the law a little bit easier if we're using a ray of light. So anytime we want to talk about a wave interacting with a surface, we need to draw normal to that surface because all angles are always measured with respect to the normal. With sound, it wouldn't matter so much. We could measure an angle with the surface, and we got it. That's okay. But with light, it would make a huge difference because the surface for a light wave, a sound wave is large. So if you have some imperfections in a surface, the sound wave doesn't really notice. But for a light wave, the light wave interacts with such a tiny, precise point on a surface that it matters an enormous amount whether that surface, what angle that actual surface is on. So we solve the problem by measuring all angles with respect to a normal. And a normal, of course, just means 90 degrees. So the law of reflection is easy. The law of reflection is that the angle of incidence equals the angle of reflection. That's it. That's the whole law of reflection. So if it's that easy, now we have to try to see if you're really sharp and you're paying attention, okay? What are all angles measured with respect to? Did you say the normal? Good. Then maybe you won't get caught up on the tricks. In any case, here we have light coming in. And let's call this 40 degrees here. How is it going to be reflected? Well, it would be reflected at 40 degrees. Do you notice that I measured with respect to the normal? So how can I mess you up on some questions with this? Well, let's see. You know the angle in equals the angle of out. So tell me in this case what the law of reflection is. You always got to be careful when something is really simple because that often means you can be tricked easier. So if I have now a ray of light coming in 20 degrees here, what's the angle of reflection? Well, because you see 20 degrees there, a lot of people, as you could imagine, would say, 20 degrees in, 20 degrees out. Well, the question would be right away, did we measure it with respect to the normal? That's the rule. So if it's 20 degrees coming in, no, it's not. That's the angle with the surface. What's the angle with the normal? Well, out of 90 degrees, what part is 20, right? So how many degrees are we missing? Well, so this has to be 70 degrees. That was your actual angle of incidence. So what's your angle of reflection then? Sure, there's a 20-degree angle here, but that's not the one you report because that's not the angle of reflection. 70 degrees, that's the angle of reflection. So they can't trick you that many other ways, but angle in equals angle out, but measure them with respect to the normal. Okay, so that's reflection. When we see reflection, it's telling you a lot about the surface, especially when we see it with light. Why doesn't this blackboard reflect? Certainly, a lot of the light hitting it is bouncing off. So why isn't it a nice reflection? Well, if you think about it, what can we do to the blackboard that would give it a nice reflection? Some of you probably immediately thought, well, when we clean it off with water, for a little bit, while there's water on it, you have a nice reflection. Well, what does water do on the surface? The surface tension on the water makes it nice and tight, makes the surface very, very flat. So is that the problem? Is this simply not flat? It looks flat, And indeed, to a sound wave, it would act flat, but a light wave is so tiny that when it hits that surface, any imperfection means that the normals are not aligned together. And if the normals are not aligned, you're not going to get anything like a real reflection from it. If you look at the floors in this school, when you come in September, are absolutely shiny as can be. What did they do to the floors? Well, they waxed them, and then they polished them. And when you polish them like that, you have a layer of wax down, and then you polish it, and you make that absolutely smooth, so the normals are all aligned. That floor then has a good reflection on it. Should also make you right away aware that that floor has very little ability to give you friction when you're walking on it. So like if you come in from outside and your feet are wet at all, this is a really slippery floor. Later on in the year, when the floor has gotten beaten up by thousands of feet walking up and down it, the normals are no longer aligned because it's all scratched and grooved, which means you don't have a reflection in it, but it does mean you can grip it a lot better. So this would be an idea of this. Consider also driving. When you're driving, this is kind of cool. When you're driving, how is it that you can see anything in front of you? When you're driving at night and you're using your headlights, how can you see stuff in front of you? Well, here's your car, the front of your car. Here's your headlights shining out in front of you on the road. Well, if the road was flat, would you be able to see anything? You realize, no, you wouldn't. No, because that light would just bounce up and go away from you. So how do you see anything? Well, you see stuff because at a microscopic level, the road is really like that. So sometimes the normals are pointing almost right back at you. So that when you hit them with light, the light coming in along this normal bounces out about the same way. So in other words, it's the roughness of the road that allows you to see it at all at night. Do we have any examples when you really can't see the road? Well, what would make the road absolutely smoothly flat? I think you can see it. Water. When it rains and you're trying to drive at night, you may realize you really can't see the road. In most cases, the road becomes virtually invisible. You're driving as an act of faith. That completely black object in front of you, that's the road. It's wet. Furthermore, oncoming traffic. They have two headlights. On a wet road, how many headlights do they have? Right. You're getting the reflection of those headlights. The driver, the headlights are darn near useless, but they're blinding you. So driving at night for multiple reasons is really challenging because of the law of reflection when it's wet. Driving at night when it's not wet, you get enough reflection back because of the roughness of the road. But when it's wet, water smooths out the surface. So the normals are all aligned, and the light hitting them bounces out, and you can't see anything. Right? So good to know the law of reflection and how this all works. Now let's move on to refraction. And interestingly, we'll apply it to driving as well. As a matter of fact, the model we're going to use for refraction has everything to do with driving. Is in fact included in about half of the fatal accidents of generally people under 25 who have not experienced this before, because it's such a ridiculous thing to happen that you're absolutely not ready for it. So to do refractions, I use something called the Jeep story, and you'll understand, I think, how it works. So let's try refraction. Imagine you have a road here. It's mud on the side, pavement up here. Now, if we're talking light, when we start talking about light, I will refer to things as optical pavement and optical mud. Well, where does a car go faster, on pavement or mud? I think you would agree pavement. So anything like that, when I say optical pavement, I mean in this particular substance, light moves quite quickly. Optical mud means in this substance, light moves quite slowly. That's all. So let's consider a car that is drifted to the side of the road. This is refraction. So here is a car that is being driven and it's just gotten to the side of the road, just like this. This tire is in the mud, this tire is in the pavement. So let's draw normal at the point of intersection here. Now the question is this car going to be pulled towards the mud or repelled from the mud? So if it's pulled towards the mud, it's going to angle down and it's going to angle toward the normal. That's how we would express it. If it is pushed away from it, it would angle away from the normal. So what's going to happen? Well, this tire in the mud, faster or slower? I think you'd agree. This tire is moving slower. This tire is moving faster. So this tire rotates down like that. And the whole car is turned down into the mud. So if you're driving along and you drive off the side of the road, you'll find your car immediately being pulled onto the side. Well, how do you correct for that? And herein shows up why this is an extremely fatal accident waiting to happen. So let's consider what this driver would be doing next. And the driver now has his car on the side of the road like that. Which way are the wheels facing in order to keep you going straight? This is where it blows your mind. You're not thinking of this. But your wheels have to be pointing like that. The wheels have to be turned already just to keep you straight. Because this wheel is going slower than that wheel. So you have to turn your wheels a little bit. But if you're going straight, which way do you think your wheels are going? You mentally picture your wheels going straight. How do you get back onto the road? Now, you've just drifted to the side. No reason to slow down or anything like that in your mind. You're about to have a fatal collision. The reason. In order to get back onto the road, you have to turn your wheels even more to the side. And the moment that the mud wheel connects with the pavement, your car drives directly across the road. When you read a newspaper article about that fatal collision, you'll hear it as an overcorrection. And it will drive your car immediately. You really can't do anything about it at this point. It'll immediately drive your car into oncoming traffic. And that might be the end. If there is no oncoming traffic, it will still drive your car across the road. You will turn very sharply and quite possibly flip your car right over. Again, quite the problem. So if you understand refraction effects, it might save your life. So what do you do in this situation? Well, wouldn't it make sense? Slow way down, basically stop. Let the traffic clear on both sides, pull back out onto the road. Safe. You get home, I bet you don't even remember to say anything when you get home about how you almost died. So it's very useful towards keeping you alive. But let's just work the Jeep story a little bit more, shall we? Now that you're going to live to be in college and all of that. So anytime you have a refraction situation, all right, what if you have a Jeep heading in, a Jeep that's in the mud heading towards the pavement, okay? Heading up here, when it gets here, all right, what's going to be the situation? Draw the Jeep in a different color. What's going to be the situation? Well, you have a tire here and a tire here, all right? And this is the mud. I'd call it the Jeep story because Jeeps like mud, so you could play in both. Well, this tire is going faster, right? So in this situation, Here's the angle that it's coming into. Is it going to bend up towards the normal or away from the normal? Well, you can see with this tire going faster, you're going to be bending away. This will move it like this. While this is like this, the whole car will be turned away from the normal. So, like we were saying, it's hard to get onto pavement from mud. So anytime you're trying to figure out what refraction is and how you're going to be using it, think of the Jeep story. Well, refraction occurs all over the place. Let's look at a really interesting effect of refraction that I personally had happen to me when I was living in Jeffersonville. There was a day I'm sitting on the porch, or standing on the porch, and I'm flipping burgers on the grill and thinking what a lovely town this is. For so many reasons, I just love this town. And one of the sweetest things is the train coming down the middle of the town. And I realized, we don't have a train coming down the middle of the town. Well, how come I'm hearing a train coming down the middle of town? All right, the nearest train is in Callicoon. And so this turns out to be an example of sound refraction. Here's Callicoon. Here's the train. Choo-choo train here with a loud whistle on it. Woo, woo, right? There is a mountain in between. I may have exaggerated the mountain, sorry. And over here is the village of Jeffersonville. Well, what were the conditions when I heard this? It was a beautiful summer day. The sun was just going down. Sky was clear. Okay, so we need to know some earth science for this. Anything that absorbs radiation really good also emits radiation really good. Anything that does not absorb radiation well also won't emit it very well. All right, so the sun is just going down. All day long, the sun has been heating up the mountain. With the sun going down, what does the mountain do? Radiates that heat away. So what we have is a layer of warm air up here. But right next to the mountain, the air is chilly as can be because the sun has just gone down and the mountain is radiating its heat away and also cooling a layer of air a little bit above the mountain. What is this going to do? Well, sound moves faster in warm air than in cold air. So let's see what's going to happen. From the choo-choo train, here comes the sound moving faster in warm air. And you can see the waves working just like this, refracting right over the mountain. And I tell you, when I heard that train, the reason I thought it was in town is because it was loud as could be. That refraction was just perfect. So why don't you hear that all the time? Is this a typical situation? Is this gonna happen all the time? Once nighttime really gets into it, well, the air everywhere is pretty cool. You're really not gonna have that refraction effect. But right as the sun is setting, the air is still very warm above it and gets quite cool on the mountain. And you have a little bit of time where that refraction effect makes a big difference. So you hear stories of ghost trains and ghost ships and odd things that people hear really close, but there's nothing there. And very often they would jump to the easiest possible explanation in their minds, which is ghosts. Well, now you see a much easier explanation. You don't need to rely on ghost trains and ghost ships. It could be, and almost certainly is, refraction. And refraction of sound is such an odd thing, you really don't expect sound to refract. Consider another situation where sound refracts a lot. So consider a baseball field during the day. Right on the ground, it's really hot and it's cool above it. So if somebody is standing here calling to you, what happens to the sound? Goes faster in hot air, so the sound goes up. It doesn't go to you if you're standing on the other side of the baseball field, hoping for some direction. So next time you're out on a hot field during the day, notice that sound doesn't travel across it very well. A situation that I had when I was a kid that was always sort of fun was on the river. Okay, and on the river, during a hot summer day, it's really cool by the water. And it's warm above it. So people in a canoe on the river talking to each other, there's a canoe facing you, deal with it, right? And they're talking, the sound waves are carried beautifully right to the bank. So if you're sitting on the bank of the river, you can hear everything going on in that boat. You hear the gentle banging of the paddle against the side of the aluminum canoe. You hear everything the people are saying pretty clearly. Although the river rustling, you can hear a lot of sounds from the river. That might make it harder to discern the conversation, but not that hard. The conversation really carries. On the other hand, during the day, or rather at night, on a lake or a river, shouldn't be out on the river at night, but if you're on a lake at night, now what's the situation? You'd see right next to the water, now it's warmer than it normally would be, and it's colder above. So the sound on a lake at night is carried up, just like that hot field. So refraction really messes with sound a lot. Refraction also messes with light. We'll get into how to work out the specifics of refraction of light. One more effect though, diffraction. If I go outside the door of the classroom, go down the hallway a little bit and say, hey, can you hear me? Yeah, people in the classroom can hear me. Then I'll ask what they consider a dumb question. I'll say, hey, can you see me? No, we can't see. Of course, you can't see around doors. Well, then how come you can hear around doors? It's the same effect. Why can't you see around doors? Here's the thing. A sound wave that you produce is somewhere on the order of like this long. How big is a doorway opening? About that long. So when you consider a doorway, let's take a look over at the doorway here, shall we? All right? So when you consider a doorway, it's easier to think this if you have a water wave. If we have the whole place filled with water, and we have a water wave passing through the hallway, and its wavelength is similar in size to the doorway. When the big lump of water gets to the doorway, it won't be like a wave passing through. It'll be like in the room the water is this high, but in the doorway the water is this high. Well, what would happen if we suddenly have a big lump of water? It would rush into the room and it would make waves in the room, semicircular waves in the room. And those waves would propagate all over the room. So even if you're in the back corner, you'd feel those waves. That's why sound waves work like that. But how big is a light wave? A light wave is really tiny. So would a light wave be able to diffract around a doorway? This is diffraction. A light wave would not do that. But could you get a light wave to diffract around something? Well, the idea is, here's an opening. Here's waves coming up to the opening. The opening now suddenly acts as a source and sends these waves out like that. Well, light certainly diffracts. Can't see it super well here, but you get a rainbow effect in this glass. It's called a diffraction grating. All right? There's thousands of lines cut into it. And so light, being super small, diffracts beautifully with that. You can see light diffract if you take your fingers, put them in front of a light source and get them really close together. When they're just about to touch, you'll see a bizarre thing that between your thumb and index finger, all of a sudden they seem to connect. Why would they do that? That's a bizarre optical effect. I'm sure you've seen that before, but we tend to ignore things that we don't understand. Now you can understand it. You made an opening so small that light begins to diffract, bend around that. So you have diffraction both of sound and of light. Why doesn't light diffract around the doorway? Turns out that's not a stupid question. Light doesn't diffract around the doorway because the opening is way too large. That's why you can't see me. Okay, so diffraction also plays with both sound and light. Okay, reflection, sound and light. Refraction, sound and light. They all do this stuff. I wonder, are there any effects that don't occur for sound that do occur for light? We'll get there. Hey, thanks for watching. See you next time.